Alright, here I want to go through some more discussion on indicial notation, but now we want to extend this to vector calculus. So a lot of the operations, the methodology behind using indicial notation is very similar here, except we're not doing or applying this method to things like dot product, vector product, cross product, etc. We're doing this on operations, particularly gradient operations. First one, probably the most important one to remember, is the novel operator. So in indicial notation, it's shown here where this is a spatial gradient in the xi direction, and of course it's a gradient in a particular direction, so we have a unit vector e hat I. So this is my dyadic notation. We have two i's. We're going to sum over 1, 2, 3 for 3D, giving us gradients in all three Cartesian directions. Second one that's important, shown here. So we can take the dot product on this novel operator. You do this very similar to what we've done on the dot product of two vectors. So you notice we have two unit vectors here, e hat I, e hat j. The difference is we don't have constant components out front. Now we have these derivative operators. So these work a little bit differently. We can bring these out to the front as shown here. We take the dot product on the unit vectors, you get a Kronecker delta. So then we can collapse this, and this gives us a second order derivative. So that's the first important thing to notice. These two derivatives collapse to second order gradient, and it's a dot product on two vector-like or vector operators. So now this is a scalar. So one that you're very familiar with, or should be, is the Laplacian operator. So this here is often called del squared. So you can write it in this form. Here I'm operating on T, as in if this was a temperature problem, is equal to 0. Similar, if this is electrostatic potential, you'll often encounter problems like that in electrostatics. The second important one is if we take this operator on a vector, could be also, you could take it on a higher order tensor, but let's just consider this operation here, which is known as the curl of V. It operates very similar to when we take the cross product of two vectors, except now you introduce the permutation symbol, and we're taking a gradient on that velocity in the k direction, gradient in j. So comma j, remember, is my spatial gradient, and it's in the e hat I direction. Here's your I on the permutation symbol. Here's just that notation. And here's how you expand this out. I can also write the gradient in this form. So this partial I is equivalent to the partial xi shown here. Take the cross with bj, so we get this operator, and this cross on the unit vectors is equivalent to this. So we get the same thing that I showed here initially. Other one I want to show is divergence. So we can take divergence on a vector. This is, as an example, this would be if that is equal to 0. So this divergence in general is not always equal to 0, but this is a particular case of an incompressible fluid is one where this often comes into play in low Reynolds number flow, but you can have other situations anywhere where there's incompressible flow. So if we expand this out, we get V I comma I, and it's shown here. Gradient operator, we dot it with the vector, so we get Vj comma I, Kronecker delta, eliminate the delta, we get vi comma I. Same thing on a tensor. So let's say we have stress, divergence of my stress. This is an example where this happens to be linear momentum for static problems. This doesn't, in general, as a mathematical operation, is not always zero. Dyadic notation, we get this form. So here's how we expand it out. We have our gradient operator, second order tensor, stress. Here's the gradient on that stress, and we take the dot product on E hat j, E hat I, right here. It's my Kronecker delta ji, E hat k, and in the end we eliminate that Kronecker delta and we get this form.